All right, today we're going to discuss addition of whole numbers. It sounds pretty basic, but remember, as teachers, you have to be able to teach addition to elementary school kids who know nothing about numbers or how to add things. We're going to look at different models today. Models are simply different theories on how to solve addition problems. The first one we're going to talk about are sets. The set model. Remember what are sets? That's what we talked about in the last chapter. What are sets? What defines a set? Right. So you have a letter, for example, set A is defined by the elements X such that X is an element of, say, the integers, and X is less than, or X is between -2 and 4. What's the difference between a whole number, an integer, or a counting number? What's the difference between those three? Very good. Counting starts at 1 and it goes on to infinity. Whole numbers starts with a whole and goes on. What about integers? Where do they come into play? Yep. They could be negative, they could be 0, and they could be positive. They just cannot have decimals. So when we deal with set model, let's say that set A contains the numbers 1, 3, 5. Set B equals the set 2 and 4. Since they have nothing overlapping, these two sets are called disjoint, since they have no overlapping. They have nothing in common. So what we're looking at here is set A is 1, 3, 5. Set B is 2, 4. A plus B, which is also the union of A and B, is a set 1, 2, 3, 4, 5. So remember, these are the numbers we can use. Now, how can we relate addition, the true definition of addition, to sets? What does that represent? That stands for the cardinal number. So what does the cardinal number represent? The number of elements in the set. So what is the cardinal number of A? The number of elements. So it's 1 through 5. Yes, that's what set A is. But what's the cardinal number, the cardinality of it? The number of elements in the set. What does that statement mean? Because there are 3 elements in set A. In set B, we have how many? 2. So we can add the 2 numbers, 3 plus 2. Which equals what? There are 5 elements. So looking at sets, if A and B are sets, not, well, they can even be empty sets. Let's say that equals A. That equals B. Then if I add the cardinalities, what that really means is I'm finding the cardinal number of the union of the 2 sets. If you look at this number, this represents number 3. This represents number 2. So 3 plus 2 is 1, 2, 3, 4, 5. Represents 5. So that's how we define them with sets. Because remember, I told you that sets and logic came way before mathematics. That's where it all came from. So this is how they determined what algebra was really a bit like. We have 2 symbols. This is a history lesson. We have 2 symbols. They were not really invented until the 1400s. Because up until then, they just combined them with the union symbol or the intersection symbol. This symbol here was a shortcut for a French word, et. 3, 4. That means 3 and 4 is 7. So instead of making that, they just took the T and condensed it. That's where the plus sign came from. And about 20 years later, this symbol had its definition, the subtraction symbol. Originally, it was M, which meant the difference or less than. And how did you find this difference? 3 remove 2 gives you 1. That's a little history lesson. So when we take algebra, we learn M stands for the formula for slope. Why is this symbol represented for slope? Because the formula for a slope is the difference between the X values and the Y values. But we'll talk about that when we get to algebra. All right, so that's the first one. We have set theories. We're using the cardinal numbers of sets. So the next thing you can use to define addition is the number line. What does the number line represent? If we're dealing with counting numbers, I should start from here, so that's 1. Because this first box represents 1 unit. This second box represents 2 units. This third box is 3 units, and so on and so forth. So in addition, how do you prove 2 plus 3? So we first, from our beginning, we go 2 spaces. Then from there, we move 3 more. 1, 2, 3. So 2 plus 3 equals 5. This is the way kids are first introduced to really the concepts of addition and subtraction in elementary school using a number line. We're going to discuss these in a little bit, but how do we prove? So this equals 5. Let's stick with this equals. So we go 3 spaces from the first one. So 1, 2, 3. Then from that end, we go 2 more. 1, 2. So what do those 2 show us? What do these 2 show us? Yeah, doesn't matter how you arrange them. As long as the same numbers and the same sign is used, you'll get the same answer. In addition, doesn't work for subtraction. This has got a name also. We'll talk about that name in a little bit. Ordering whole numbers. What does it mean by ordering? By ordering, we know we have the sequential number of numbers, but now we discuss the concepts of less than and greater than, or inequalities. The statement A is less than B. How do we write that algebraically? What symbol do we use? Which one? Not the parentheses. A less than. What's the less than symbol? So where does it point, left or right? It always points to the smaller number. Actually, less than. Look at the number line. Here's -2, -1, 0, 1, 2. Less than. Less than always goes this direction. So these numbers are all less than the one before it. I'm pointing to greater than because these numbers are bigger. So that's one way to look at it. Less than points the direction of lesser numbers, smaller numbers. Greater than points to bigger numbers. But we always read left or right. So what symbol do I put here for this one? That symbol. Now, how do we prove that one number is less than another number? It's got to be done mathematically. A is less than B if there is a number K, which is greater than 0, it's positive. Where A plus K is equal to B. So now, what does this mean? Why does this prove that A is less than B? Well, because listen, if this was A, are A and B equal? Which one's less, A or B? A. Why is it less? Because how do I go from 2 to 5? What do I have to do? You have to add 3. So that's my K. This is my A where I begin. I have to add 3, then I get to 5. So I have to add something to the first one to make it equal the second one. Therefore, it's less than. That's the definition, the math definition of it. So if you look at number 9, you have 2 numbers. The farthest to the left is A, the farthest to the right is B. How much do you have to add to go from one to the other? So to go from 2, I have to go to 1, 2, 3. I have to add 3 more spaces. So we have 2 plus 3 equals 5. This is A plus K equals B. So that's how you prove inequalities. Then we also have these two. What do they mean? Or it could be equal to. Yeah, so on a number line, A equals B. So here, A, can we say A is less than equal to B? First off, is it less than? Is A less than B? Because it's to the left, yes. Can they be equal? Well, which that means is I could rewrite them like this. So if I can do that, if A and B can have the same value, then I use the inequality, the strict inequalities with equal sign underneath it. Yeah, but it all depends on how you define A and B. If A is just the numbers 1, 2, 3, and B are the numbers 5, 6, 7. Is there any number I could choose where this would be true? Are all these numbers less than these numbers? Can they be equal? No, this is numbers 1, 2, and 3, 5, and 6. So they can't be equal. These two sets are strictly unequal. They can never be equal. So these numbers are less than those. But they have one, or at least one overlapping, so they can be equal. So any number I choose from here is less than or equal to any number from here. All right, so let's look at some ways we can show all this stuff. First method is counting on. This is how we first teach kids how to add. When we teach them to add 3 plus 4, what's the first thing they do? They count, they count to 3. 1, 2, 3. And then from 3, they count 4 more numbers. 4, 5, 6, 7. So here are my 3 numbers, and here are my 4 numbers. Since I end on the number 7, that's the answer. That's what counting on is. So you start by counting how many you have the first number, and from that last number, you count how many the next set is. So what these represent are not really numbers, they represent how many numbers. From 0, I would have to go 3 spaces. 1, 2, 3. From 3, I gotta go 4 more. 1, 2, 3, 4. So it's 4, 5, 6, 7. So the answer is 7. That's the first one. The next one we have is called doubles. With this method, we first teach the kids 1 plus 1, 2 plus 2, 3 plus 3, and so on and so forth. Because once they understand these, then addition of any other numbers are pretty easy. So let's say we had 6 plus 6 equals 12. We know that from our doubles, 6 plus 6 equals 12. So 6 plus 7 . What's 7 made of? How do we get from 6? How do we get to 7? Yeah. So 6 is just 6. 7 is 6 plus 1. Now, since I have 2 6s together, and I know that 6 plus 6 is what? We know it's 12. 12 plus 1 is 13. So that's another way you can teach kids. Let's try that one again. 5 plus 8. Do that one using doubles. So what number are we going to pair up here? 8 is made up of what? 5 plus 3. So we do the 5. What is 5 plus 5? And then 10 plus 3 is 13. So you pair off with the smaller number. Let's do one more. 7 plus 8. The smaller number, leave it alone. The bigger number, how far is it from 7? So 7 plus 1. We pair off the doubles. 7 plus 7 is 14. 14 plus 1 is 15. See, so in addition, all you have to do is teach them the doubles, which is there's only 9 of them. 1 plus 1, 2 plus 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 9, 9. Or 8 of them actually. And then from there, it's either add or subtract up to a few numbers. The third method is called tens. make the two numbers equal 10, then add the extra numbers to it. Let's look at 7 plus 8. We can either start from 7. 7, how do we go to 10 from 7? What do we have to do? Yeah, so we break down 8 into 3 plus 5. Now, if we add 7 plus 3, that equals 10. 10 plus 5 is 15. But 8 plus 6. Well, let's do it both ways. So it doesn't matter which way you put the numbers. Since 8's first, let's break this one down. So what to 8 equals 10? So 6 is made up of 2 plus 4. 8 plus 2 is 10, plus 4 is 14. Now, let's look at the second side. What do you have to add to 6 to equal 10? Yeah, so we need 4. So 8 is made up of 4 plus 4. So 6 plus 4 is 10. 10 plus 4 is 14. So that's how that works. Basically, you're adding to the easier number and then going from there. Typically, people have a hard time adding 7s and 8s. Any numbers plus 7 and 8, those are most difficult ones students have trouble with. All right. Probably properties of addition. We're dealing with whole numbers still. Closed or closure. Adding any two whole numbers will result in a sum that is a unique number in the whole number system. I could have said result in a unique whole number. I could have said that, but I worded it out. So what does that mean? If it's closed, and if I add two whole numbers together, will it give me a decimal? No. Are decimals in whole numbers? No. So that's what closure means. If I add two numbers that are whole, the answer is going to give me a whole number. That's all it tells us. All right. Here's the closure property. Of the addition of whole numbers. This is the actual property now. Let A and B be any two whole numbers. Then A plus B results in a unique whole number. That's the theorem. What's an example? Is 5 a whole number? Yeah, no decimals. Is 5 a whole number? Yes. They equal 10. 10 is a whole number. 3 plus 4. They're both whole numbers. They equal 7, which is also a whole number. That's closure. In other words, I could never equal something that's a decimal. Is this closed under the closure property? What does it mean? What two times X? What is X? X is an element of the whole numbers. So for example, 2 times is 4 a whole number? Yeah, 2 times 4 equals 8. Is that a whole number? Yes. So that's a true example of closure. If I multiply any whole number times 2, the answer will be a whole number. In other words, it will not be a decimal. How about if I do this? If I subtract 1, will it give me a whole number? Yeah. Pick a whole number, let's say 4. 2 times 4 is 8. 8 minus 1 is 7, and 7 is a whole number. So yes, that one passes that example. It shows better on a number line. If the two numbers you pick and add together, if they're all on the number line, those are all whole numbers. Let's look at those two properties, or two examples. We're looking at 2x and 2x minus 1. We're looking at those two examples using a number line. How would you teach multiplication to your kids? What is multiplication? Multiple times, not multiplied. Yeah. So what we have here is we have the number 2 3 times. So it's 2 plus 2 plus 2. Or we could say we have the number 3 2 times. Multiplication is simply a turbo addition. So they both equal 6. So how would you prove this with a number line? So start from here. 1 2 1 2 1 2 1 2 3 4 5 6. Because the answer is a number on my number line, it's a whole number. Two, 3 4 5 6. So look at this one. 2 times 2. So we start with here. 1 2 1 2. That's 2 times 2. That equals 4. Now I got to subtract 1. The answer is 3. Is this a whole number? Yes. Well, we've shown so far that, for example, 3 plus 6 is the same thing as 6 plus 3. That a true statement? Yeah, if I start off at go to 3 spaces, 1 2 3, count 6 more. 1 2 3 4 5 6 2 3 4 5 6 7 8 9. Or if I go 6 and then add 3, I end up with 9. So this property, because I'm moving around, is called the commutative property of addition. Commute means to move. So what this property says is I can move the numbers around without losing the answer. We've also seen examples like this. Here's 7. There's 8. Whenever you have 3 or more numbers, you have to tell me which ones I'm going to add together first. That's what the parentheses are all about. The parentheses tell us what 2 do you combine first. because of that, since we're grouping them, this is called the associative property of addition. We're associating. We're grouping two numbers first. And we also can show that how would you do this on a number line? Yeah. You start at 0, move over 4 spaces, 1, 2, 3, 4, and don't go any further. So you end up at 4. Nine plus 0 equals what? Yeah, so anytime you add 0 to a number, it doesn't change it. That's called the identity property of addition. Of whole numbers. Why is it called the identity property? Because 4 keeps its identity. It doesn't change. All right, so let's look at the examples here. I'm going to give you 4 statements. You tell me which properties proves these, or which ones they represent. These are the 4. So tell me which properties these demonstrate. How about the first one? 5 plus 7 equals 7 plus 5. Yep. How about the next one? 1000 plus 73 is a unique whole number. Yep. It's a closure. Because these are whole numbers, and if I add them together, it's a whole unique whole number. That means it's closed. How about the next one? The only thing we changed was inside the parentheses. So this is also commutative. And the last one. Okay, this one to this one, I just moved them around. I put the parenthesis afterwards. So this is commutative. Did I do anything else over here? From here to here? I changed the parentheses. When you change the parentheses, what's that called? The associative, right? Properties. What's funny is here we're discussing this stuff for elementary school kids. The first week of college algebra, we talk about these. Actually, the first day of college algebra. Because these rules apply no matter what math class you ever take. Moving numbers around. Addition algorithms. What's an algorithm? I know you've heard the words before. What's an algorithm? It's basically a plan. It's a roadmap, a step-by-step description of what you should do. Computer programs are called algorithms because the computer has to follow these rules as it goes along. So that's what an algorithm is. What this one says is, let's pretend we have (47 plus 33). How can we show a one-step method that would prove this and then solve this that we can use on any other equation? One example would be using manipulatives, those little blocks. What does 47 represent? Look at the place values. We have 4 10s and we have 7 1s. Because this is in the ones column, this is in the tens column. So we have 7 individual small boxes. And 4 10 by 10 sheets of blocks. Each one of these contains 10. Oh, that's not a sheet, I'm sorry. These should be a bar. These are bars. Each bar has 10 ones in it. Y'all remember manipulatives like this, blocks? You start off with 1. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10. 2, 4, 6, 8, 9, 10. So there are 10 rows and 1 column. So 10 times 1 is 10. This one has 10 columns and 10 rows. So it's how much? 10 times 10 is 100. So using blocks, we have, so for this one, we have 4 strips or bars. Plus 7 squares. I made it plus, plus the 33, I have 3 bars. And then 3 squares. Since I'm combining them, I take these 4 bars and these 3 bars. I got those. And then I got these 7 boxes and these 3 boxes. So far, so good. But since these single boxes equal 10, we can trade them up for a bar. Because in a bar, there's 10 boxes. So this one becomes a bar. How many bars do we have? 1, 2, 3, 4, 5, 6. We should have 7 here. And that one makes it 8 bars. How many are in a bar? 10. So 8 times 10 is 80. So this is my 4 from that one, my 3 from that one. And this one, once I have 10, I can make a bar. That's how you teach kids how to use manipulatives. It works great with addition or subtraction. Another method that we can use to teach kids is by breaking down these numbers. This is in the tens, so we have 4 times 10. And this is in the ones, which is just 7. So let's do that to both of these. We have 4 times 10 plus 7, 3 times 10 plus 3. If we drop the parentheses, since there's no number in front or no minus signs, we could move them around by commutativity. So I'm going to group together the tens. I have 4 times 10 plus 3 times 10 plus 7 plus 3. So I have 4 tens here and 3 tens here. I can combine the coefficients, the numbers in front. 4 plus 3 is 7 times 10. 7 plus 3 is 10. So how many tens do we have? Here's 7 of them, 7 times 10. There's 7 of them there. Because if we drew all these, it would be 7 or 10, 10, 10, 10, 10. So there's 7 tens there. And we have one more 10. So we have 8 tens. These 7 and this 1. What is 8 times 10? So that's another way you can teach them. This method is called combine like terms. Because the 3 and the 4 are like terms, they're both tens. So I combine those. Now it's 7 times 10, 1 times 10. They're like terms, they're both tens, so I combine those. Where else would you see something like this? This is a more prevalent way where you see it. Combine like terms. Write them on top of each other. So x squareds are here, so it's 4x squared. The x's are the next one, and the ones. How many ones do we have? 5 plus 1 is 6. How many x's? 5 plus 3 is 8 x's. How many x squares? 4 plus 2 is 6. So there's that solution. That's combining like terms. These are all terms. A term is anything separated by a plus, minus, or equal sign. That's what when we say like terms, that's what we're talking about. Another method is called partial sum. $365 plus 231. Partial sum is just this. Take each numbers. So we have on the top, we have 300. That's that one. Plus 60. That's that number. Plus 5. That equals 365. This one, we have 200 plus 30 plus 1. You see why I call it partial sums? Because I'm taking parts of each number. Now I'm going to add those. 300 plus 200 is 500. 60 plus 30 is 90. 5 plus 1 is 6. Now combine those. Or you could do it straight down. In the hundreds, we have 3 plus 2 equals 500. In the tens column, we have 6 plus 3, which is 90. And in the ones, we have 5 plus 1, which is 6. Add each one of those. I'm using the same numbers. Because you see how we start with the hundreds, tens, and ones? This is called the left side or left-sided partial sum. I start with the numbers on the left side and work my way in. Or I can start with the right-hand side. The ones, 5 plus 1 equals 6. The tens, I have 6 plus 3 is 9, so it's 90. Hundreds, I have 3 plus 2 is 5, times 100 is 500. So this is the right hand. Right-sided. Okay, we have enough. Another method is called the lattice method. $48 plus 35. What you do here is on the bottom, we create a lattice work. Here's the ones, here's the tens, and there's 100. So each one of these, so 8 plus 5 is what? 13. So yeah, the 10s go on top, the ones go on the bottom. What does 4 plus 3 equal? Yeah, so there's no 10s and 7 1s. To get the final answer, you add all the numbers in these diagonals. So this is a number 3. 1 plus 7 is 8, and then 0. So the answer is 83. So we have the 1s, the 10s, the 100s, the 1000s. And you just put diagonal lines in here. So the first one, 8 plus 9 is, so it's 1 and a 7. 8 plus 6, 14. 2 plus 7, so it's 0, 9. And 4 plus 5, 0 and 9. So we add each of these diagonals. So 7 is the first one. 4 plus 1 is 5. 9 plus 1 is 10, so I put the 0, carry the 1. 9 plus 0 plus 1 is 10, carry the 1. And then 1. So the answer is 10,057. Any questions?